NASA's Jet Propulsion Laboratory presents the Von Karman Lecture, a series of talks by scientists and engineers who are exploring our planet, our solar system, and all that lies beyond.
Good evening, ladies and gentlemen. How's everyone tonight? Excellent. I really want to thank you guys for coming out tonight, especially in that weather. We didn't expect a house anywhere near this full, so thank you very, very much. So, shall we? Mission planning is a core strength of JPL engineering, along with deep space communications and navigation. Tonight, we're going to take a look back at the various scenarios and contingency plans that the Cassini team made as they steered the spacecraft into unexplored space during its 2017 grand finale. Our guest will discuss how the possible scenarios, some of which could have been mission-ending, compared to the mission as it was actually flown, along with sharing some science highlights from the finale. Tonight's guest was the mission planning lead for the Cassini mission. Prior to joining Cassini, he served as a mission engineer and mission architect for the Mars Advanced Formulation Office and for other various planetary mission concepts. He joined JPL in 2005, fresh out of Cal Poly San Luis Obispo, where he received his BS in aerospace engineering, a BA in physics, and a master's degree in aerospace engineering. Ladies and gentlemen, please help me welcome tonight's guest, Mr. Eric Sturm.
Thank you very much, and let me second the thanks for coming out in the rain. That's very impressive. Thanks to the smarter ones who are online, who are watching from a nice, warm, dry area. Okay, so yeah, as was said, I'm Eric Sturm, and I am Cassini's lead mission planner. And I say am, not was, because while the Cassini mission ended 6 months ago, the project is still going. We're still archiving. We're still closing out. We're still writing reports. It's not as fun as it was, but it's not past tense yet. So I have the honor of speaking to you guys tonight as Cassini's last mission planner, but I'm certainly not Cassini's only lead mission planner. And in fact, I share that title with 5 other people, and you can see them all here. And so without the hard work of these people, Cassini wouldn't have gotten off the ground, it wouldn't have gotten into space, wouldn't have made it out to Saturn, and it certainly wouldn't have made it through its tour. And let me be here tonight to talk to you about the end of that tour, Cassini's grand finale. And as you can see, Cassini's been around a long time. He first got a lead mission planner back in 1991, but the beginnings of Cassini actually go back even before that, back to 1982. That's when Cassini was born. And at that time, a working group was formed between the European Science Foundation and the National Academy of Sciences, and they were supposed to come up with a joint concept for exploring the planets, and eventually what came out of that was a concept that involved a U.S. Saturn orbiter and a European probe that later became Cassini and Huygens. And you can actually see Cassini and Huygens over there. That's our half-scale model. And just to give you more of an appreciation of just how long ago 1982 was, that's me back in 1982. So Cassini and I were born in the same year. So, yeah, it was a long time ago. Okay, so jumping ahead a few years, Cassini launched in 1997, and it followed this nice loop-de-loop green path out to Saturn. That's actually 2.5 revolutions around the sun. It flew by Venus twice, Earth, and Jupiter, all on its way out there. And 7 years later, it arrived at Saturn in July of 2004. And at that time, it began its prime mission, which was a 4-year mission to tour Saturn and explore it and its moons and the rings. It got a mission extension in 2008 to go an additional 2 years out to 2010. That was the Cassini Equinox mission. And then it did such a good job there, it got a 7-year mission extension, the Cassini Solstice mission, which was so named because it extended the mission all the way out to the northern summer solstice. And that ended 6 months ago. So here you can see the entire solstice mission trajectory. This is from when it started in October of 2010 up until the end of November of 2016. And at that time, Cassini began its penultimate phase, which were the ring grazing orbits, these lighter gray orbits that you see here. And so this was a series of 20 orbits. The farthest they get from Saturn is out near Titan's orbit, and the closest they get is just outside the ring system, Saturn's F ring. That's their name, the ring grazing orbits. So these 20 orbits took a little over a week to complete. They started at the beginning of December of 2016 all the way through the middle of April 2017. And here is the last of those ring grazing orbits. So it's the last time that it's going to pass outside Saturn's ring system. And this time, as it comes back out towards Titan's orbit, Titan's actually going to be there. And what we're going to do is we're going to perform our last targeted Titan flyby. This is our 127th close flyby of Titan. We came within 600 miles of the moon, and that changed our orbit just enough that now, as it comes back through towards Saturn, instead of being outside the ring system, it's inside. And it'll be between the planet and the rings. And so that dive happened on April 26th, 2017. So just about a year ago now. Okay, so that's what started Cassini's grand finale. It's a series of 22.5 orbits that dove between Saturn and the rings in a gap about 1,200 miles wide, and it did it at 76,000 miles per hour, which would get you to DC in about 3 minutes, or to the moon in a couple days. So it was going pretty fast. Also, periodically, as it came back out to Titan's orbit, Titan would be there, far away, not as close as the 600 miles, but it would give it a little tug and change exactly where we flew through the gap. The last of those distant flybys, which is happening right there, was on September 11th, and that's where Titan gave us a goodbye kiss. Some may call it a shove. And it actually made it so instead of passing safely through the gap, 4 days later, on September 15th, 2017, we were permanently captured by Saturn. Okay, so one of the first questions I get when I tell people that we did this, they're like, well, why did you do that? Cassini was a cool spacecraft. So first, why we had to do it at all was for planetary protection. The Saturn system has 2 protected moons, and protected just means that they have environments that could possibly be habitable for life. So one of those is Enceladus. Enceladus is pretty cool. It has a global subsurface ocean under a thick ice shell, and it's in direct contact with an active rocky core, very much like environments found near our deep ocean vents. And then there's Titan with its thick atmosphere. It has rivers and lakes of liquid methane and ethane, and both of these are thought to be environments where we could find life. And because of that, it means we have to absolutely ensure that Cassini would never impact these and possibly contaminate those environments with our own life, because the last thing we'd want to do is send a future mission there and discover life only to find out, no, that's life that we just brought when we crashed Cassini into one of them. So that meant Cassini needed to be removed from the Saturn system one way or the other. Either through leaving it or through crashing into Saturn. The reason it needed to happen now is actually because of Cassini's gas tank. We were running low on fuel. So here's our spacecraft, and this is not an engineering representation, but a good representation of our gas tank, and we're going to fill this up with gas right now. And I should say, when I asked my wife what color is Cassini's gas, she said it's orange. It's definitely orange. So we're going to fill it up now with definitely orange. It's a little like cerulean blue, but definitely orange. So there it is. And another nice thing about actually being orange, well, think of this as 100 oranges, okay? So this is 100 oranges worth of fuel, okay, at launch. Okay. Now, just getting out to Saturn, we used 24 oranges. So we're down to 76. Okay, now we want to go into orbit about Saturn. All right, well, that's another 45 oranges. Now we're down to 31. 4 years after the start of our prime mission, used another 17, only 14 left. Okay, 2-year mission extension, we can do this. 8.5 oranges. Okay, 7-year mission extension, we've got 5.5 oranges left. All right, well, we can use them all. And okay, now we have the ring grazing orbits in the grand finale for the last year. And I think you can see some propellant still in there. That's, oranges have about 10 to 11 wedges. That's a common knowledge, right? Okay, that's 1 orange worth of fuel, or 1 orange wedge worth of fuel. That's how much we had left. So we started with 100 oranges. We ate 99, opened that 100th, and ate 10 of the 11 wedges. That's what we were left with. Okay, so that's what we flew the last year of the mission on. Okay, and so why did we do it by going into Saturn? Like I said, we could have tried to get out of the Saturn system, but by going into Saturn, it gave us the opportunity to collect a bunch of unique science. So we were going closer to Saturn than ever before, so we could get lots of information about Saturn's internal structure, like gravity, magnetic field. We were also going inside the rings for the first time, which would let us see their structure, possibly estimate their mass, and get an idea of how old they are. Also, because of how close we were flying through the auroras, through radiation belts, through ring dust, so we were going to get direct measurements of all of those things. And then, simply because we were so close, we'd get really high-resolution images. And these images are amazing, and these aren't even ones from the grand finale. We got better, higher-resolution images than these. Okay, so that's a long wind-up of the grand finale and why we did it. As Cassini's mission planner for the 4 years before the end of mission, I spent all my time worrying about this gap, minding the gap, so the region between the rings and the planet. And here you can see where the 22 orbits passed, and you can see the final orbit in orange that actually impacts Saturn. And you can compare that to an actual image that was taken by Cassini. And so you can see we're flying right where that D-ring dust and the atmospheric haze just sort of fade into the background of the image. So like really going right where we think it's safest. And so those really were our two concerns for these orbits. How much dust was the spacecraft going to encounter, and how thick of an atmosphere was it going to fly through? And that meant that each of the 22 orbits could be characterized by 2 points. The first was their ring plane crossings. So this is how high into the ring plane did they go, and how much dust was potentially going to impact the spacecraft. The second point was how close did they get to Saturn, their minimum altitude, how much atmosphere were they going to fly through, and how much drag and torque was going to be imparted on the spacecraft. And you can get a little better idea of how these are distributed through the gap by looking at them down from above. So now you can see Saturn down below, we got the rings up above, and you can see the orbits going through. And what's neat about looking at it in this, from this perspective, these are actually in chronological order. So the first one's on the left and the last one's on the right. And so you can see each of the ring plane crossings and the minimum altitude points. You can also see how there's the variations. And those are caused, like I said, by the distant Titan flybys that we were having periodically as we flew the grand finale. And to get a better idea of those variations, we can take all those points and plot them up. I'm an engineer. I got to put things into Excel. I can't just look at pictures. And so now we have time on the horizontal axis, starting at the end of April, going to the middle of September. Again, D-ring dust up above, atmosphere down below. And we have distance from the center of Saturn in kilometers on the horizontal axis. And I know everybody's familiar with kilometers, and 63,000 kilometers makes perfect sense to everybody in the room. But just in case it doesn't, we're also familiar with how wide the Earth is, right? So that's about 5 Earth diameters from the center of Saturn. Another very common measurement. So, okay. So these are our ring plane crossings and minimum altitudes. You can see at the end we get low in the atmosphere. But for the 17 orbits before that, we're actually much higher up, and we're more concerned about the dust environment than the atmosphere. And so we're going to start by looking at that. So what did we know about the dust environment? This is literally everything we knew about the dust environment. This is our best picture of the D-ring dust. And so what we did is we took this picture and we overexposed it, and then you could draw a line and say, hey, outside that line, there's dust. Inside that line, we're not really sure, but we think there's not dust. And if we go back to, and compare that to the range through which we flew the orbits, you can see that our highest orbits actually went above it. They went into a region that we knew there'd be dust. And so going back to our corridor chart and adding that line, we can see it was actually our 4 highest crossings. So those 4 crossings flew through a region that we knew there would be dust. And so what does that mean? Well, it doesn't particularly mean a whole lot because Saturn is a dusty place. We've flown through dust a lot before. And so whenever the dust was such that it could have posed a risk to the spacecraft, what we would do is we'd take the entire thing. Again, you could look at it over there. We'd take that huge antenna and we'd turn it into the direction that the dust was coming from. And you can see that that shields all of the spacecraft behind it. So all of our sensitive electronics and instruments were protected behind the high gain antenna. So good, we have a shield. We will use it. So there we go. Our 4 highest crossings were shielded. But then the question is, well, What about those other 13 crossings? Like I said, if we go back to this picture, we don't necessarily know what's happening inside that purple line. It could be there's no dust there, but it could be the nature of the dust is changing and reflecting less light. As an example, think about if it's nighttime and it's foggy and you're driving, you have your headlights on, the fog is just reflecting everything back at you. All you can see is fog. You can see the fog very easily. But then if it's raining, instead of foggy, you have still lots of droplets in the air, but they're much bigger and they don't reflect as much light back to you. So we couldn't know for sure if it was foggy outside and not foggy inside, or if instead of foggy, it just started raining. And if it just started raining, that meant there were large dust particles there that could pose a risk to the spacecraft. So, given that information, I know what you're all thinking. Okay, well, we have a shield. Let's just use this. We're going to Captain America this sucker, and we're good. We're done. And if you thought that, great. You'd probably make a very good spacecraft engineer, but you'd probably upset a lot of scientists. The reason being, everything on Cassini is body fixed. It can't point in two directions at once. So if we're using our antenna as a shield, it means the cameras can't look over here at this very interesting thing. And so while that may not seem like a big problem because, hey, this is only for ring plane crossing, that's just this small little piece of the orbit, Cassini is the size of a school bus, and it's not very nimble. And it doesn't have very large thrusters. And so what that means is it takes a lot of time to turn the spacecraft. And when you factor that in, the time to turn to that shielded direction and then the time to turn back to our nice science-friendly attitude, suddenly we wipe out all of our high-priority science areas. So, okay, we know this is a bad idea. But it's possible that this is a bad idea too because we don't actually know what's there. So what we did was we came up with a contingency plan that said, hey, we're going to shield that very first crossing. And when we do that, we're going to use an instrument, the radio and plasma wave science instrument, to detect the dust particles that are there. When the dust hits the spacecraft, it creates plasma waves, and that instrument can detect those waves. And from that, we can see if the environment is safe or not. But the catch here is that that first orbit and that second orbit are only 6.5 days apart. So we had to get the data back, analyze it, and decide what to do with the spacecraft in 6.5 days if we were going to keep everything else unprotected. And so this is what this looked like. So here we have our first ring plane crossing in green, coming around to the second one in red, and then we have all of our communication passes in blue out on the far side. And so after we came through that first crossing, it took a whole day before we even got to talk to the spacecraft, so that wiped a day out. We only have 5 days left. The spacecraft gave us back all of the radio and plasma wave science instrument data. And then we wanted 2 opportunities to tell the spacecraft if it needed to go to the safe attitude. And so that's what you see there, those next 2 opportunities. And had it seen hazardous dust, it could have turned the spacecraft and gone in the next one shielded. Okay, so that was the plan. That was our contingency plan. And what actually happened? Well, in order to understand what happened, let's take a step back to our ring-grazing orbits. Okay, these are the 20 orbits before the grand finale. During the 3rd ring-grazing orbit, the radio and plasma wave science instrument was on, and it took data for us. And the data it gives us is this. And what this is time on the horizontal axis. It is dust particle size on the vertical axis. And it is the density we see at that time, at that size of that dust particle. So this is how thick of a dust cloud do we fly through. And so you can see on this 3rd ring-grazing orbit, the ring crossing should probably jump right out at you. It happened right there. And on this scale of less dense to more dense, the red that we're seeing here actually isn't even dangerous to the spacecraft. So if this is what we saw when we went through the first time, we wouldn't even have to shield it. It would have to go into a nice, deep, dark maroon for us to be worried about it. So what did we see? We saw this. We almost literally saw nothing. You can't even tell where ring plane crossing happened. It happened there, but there was just no dust. And so we didn't have to invoke the contingency. The scientists, there was much rejoicing. And so this is what it looked like. And in fact, we didn't see a noticeable amount of dust until that first orbit above the line. And there, the dust wasn't hazardous. And so it turns out we did use our contingency, but we used it in reverse. And we were able to take that 3rd orbit and unshield it. And what that meant was, on the left we have the original design, on the right we have what we did. And so instead of turning and pointing straight down to look at the dust and shield us as we came in, we kept rotating past. And this let our cosmic dust analyzer peek out from beside the antenna and directly sample the D-ring dust particles. So we were actually able to get more science than we thought we were going to. Okay. So that brings us back to our corridor. And now we're done with dust. We're done with those first 17. Nobody's worried about dust anymore, right? Okay, good. No one's worried about dust. Now we're worried about the atmosphere for those last 5. And this is not the first time Cassini flew through atmosphere. Titan has a very thick atmosphere, and we flew by Cassini, I would say, lots of times. So again, 127 times we flew by Cassini. And during those low Titan flybys, we switched from reaction wheel control to thruster control. And the reason we do that is the thrusters can provide about 10 times the control authority that the reaction wheels do. And that means that we could fly through a 10 times thicker atmosphere and still point the spacecraft in the direction we wanted to point it. Now, if the atmosphere was so thick that it would overwhelm our thrusters, what we could actually do is perform a maneuver, change the trajectory, and fly through a less dense part of the atmosphere. So these are our 2 options when it comes to dealing with Saturn's atmosphere. So what did we have to do? Well, first we need to know, what do we know about Saturn's atmosphere at the time? Well, everything we knew came from solar and stellar occultations, which is having Cassini watch the sun and stars set into Saturn's atmosphere and see how their light gets filtered through it. And from that, the scientists derived a density model. So this gives us density as a function of radius and latitude on Saturn. And so we can use that model and go back to the proximal corridor and start adding some boundaries. So the first is our spacecraft capture boundary. So this is the region that we had to get to in order to ensure that Cassini would not come back out of Saturn again. And you can see the very last plus on September 15th is well below that region. Above that, we have the tumble boundary for thrusters. So this is the point where the density of the atmosphere is such that if we were on thruster control, we couldn't point in the direction we wanted to point, and we'd start to drift. And then above that, we have that same boundary, but for the reaction wheels. So this is where the atmosphere is 10 times less dense than the boundary for the thrusters. And you can see that our final 5 are right between those 2. So what that meant was we flew those last 5 on thruster control. And you also see that 2 others were on thruster control earlier than that. That wasn't because of atmosphere. It was actually because of science observations that wanted to take advantage of the higher turn rates that were allowed thanks to the thrusters' higher torque. Okay, so to get an idea of just how close we're coming to not just having to use thrusters, but potentially having to use a maneuver and get out of this region, we can zoom up on the final 5. And so here you can see about how close we're getting to the tumble point. And so we thought we had about 120 miles of margin between where we were going to fly and where we would tumble. And to get a better idea of just what this meant for the spacecraft in terms of the thrusters, we can convert that altitude margin into a thruster duty cycle margin. And so here, thruster duty cycle is the percentage of time that the thrusters are on while they're in the atmosphere. So if they're on 0%, it means they didn't really encounter atmosphere. If they're on 100%, it means they're flying through more atmosphere than they can handle, and we're about to lose pointing control. And you can see that our worst case scenario had us at just over 30%. And as a point of reference, Titan flybys, low Titan flybys in the past, were designed to have a 70% worst case. So we were even less than half of that. So we felt pretty comfortable going in. But again, we were prepared to be surprised. So just like with dust, we had a contingency plan. For the atmosphere, we had a contingency plan. So the plan was to fly that very first one just as planned. It has the lowest duty cycle of all of them. It was the highest in the atmosphere. It was the least likely to lose control. But if what we saw there was more atmosphere than we thought, we could perform a maneuver in between the 2 passages and pop up into a safer part of the atmosphere. We could then fly this blue trajectory to the end, all by performing one maneuver. Okay, so again, all of you wanted to shield absolutely every crossing. So now you're all just ecstatic, hey, we have lots of margin here, and we have a contingency plan, so we're good. We're going to sit back, relax, and enjoy these last 5 orbits. Again, you're going to upset a lot of scientists. The scientists came back and they said, well, you know, that's only 25%. You can go to 70, so you can go lower, right? Well, that really depends on how much fuel we have and what actually we saw in the atmosphere. But let's just go ahead and take a look at it. We can go lower, and specifically they want to go lower for those last 2 because those are the ones where we were doing a direct sampling of the atmosphere. And so looking at the higher of those 2, the Rev 291, now we're changing the horizontal axis. Now the horizontal axis is the size of the burn we'd need to perform to get lower into the atmosphere and to hit different duty cycles. It's in meters per second, which is speed. It's how much do we have to change the speed of the spacecraft to get lower into the atmosphere. 4.5 meters per second is about 10 miles per hour. And so as we start to change the speed of the spacecraft out near Titan's orbit, we get lower in the atmosphere, and we find that it would take about 2.25 meters per second, about 5 miles per hour of speed change in order to get low enough in the atmosphere that we'd hit that 70%, which also corresponds to a best guess, a best estimate of a 40% duty cycle. To give you some idea of the size of that burn, we're going 3,700 miles per hour out at Titan, and we need to change the speed by 5 miles per hour. So it's kind of like sticking your head out of the car window and blowing backwards to see how much speed that adds to you. So not a lot. Our one orange wedge of propellant was going to be enough to do this. So this, in fact, became a viable option. And what it meant for the scientists was, now if we're looking at change in altitude on the left and change in orbit period on the right, or the amount of time it takes to get back around to the same point in the orbit as we do different burn sizes, what it meant was they got a little over 100 miles deeper into the atmosphere, 176 kilometers, and it only changed our orbit period by 2 minutes. So all the other science observations we were doing during the orbit, other than right there where we were at the lowest point, really weren't affected, because 2 minutes over 6.5 days, not too bad. And so this became our third viable path through these final 5. All right. So now the question is, well, what really happened? So we flew through that first time, and it came in right there, 30%. And doing some quick math, that is 2 to 3 times thicker than we thought the atmosphere should be. And if you use that data point to update our model, the other predicts do this. So wow, that 70% line, we didn't fudge the numbers for that. That second one is actually 69.7%. So it came in just under it. But needless to say, the scientists were like, okay, we don't need to go deeper. And then the project manager said, hey, you know what, we're still below the line, and that's our worst case. So we're going to stay the course, and we're just going to not perform any maneuver. And so turns out that was the right call. The next 4 came in here. So you can see they were actually below what the updated model would have said. So we flew through some thick clouds that first time and scared ourselves. But they were still above the original estimates. So, and this is still a mystery. We're still trying to figure out exactly why our stellar occultations and the direct measurement of the atmosphere didn't quite line up. So going back to our final 5 chart, we can update this for where the atmosphere actually was, and we think it was about there. And so that was our as-flown final 5. And then we can back out again. Now we've done dust, we've done atmosphere, and here's the as-flown grand finale. So 4 shielded crossings instead of 5, and no maneuvers in those final 5. Okay, so that's the end of my talk as a mission planner. Now I'm going to try and play scientist, which can be interesting, or maybe just space enthusiast. That's probably a better way to put it. Okay, so some fun science stuff. So what was the result of all this? Well, first, before we even got to the grand finale, one of my favorite images was taken during the 7th ring grazing orbit. And here it's Daphnis orbiting in the Keeler gap. Yeah, you're having some trouble seeing it, huh? Here. Here's the actual image that was taken. And so here you can see Daphnis, one of Saturn's moons, orbiting in the Keeler gap between the rings in the main ring system. And you can see as the ring particles go by Daphnis, it actually creates a wake. And you can get an even better view of this by applying some false motion. And so you can see that as Daphnis orbits to the right, the rings below are orbiting slower and appear to move to the left. The rings above are orbiting faster and go to the right. And so you have a wake on the outside ring going out to the left. And on the inside ring, you may just be able to make out the start of a wake going in the other direction because of the relative motions. So, very analogous to that is this other fun image of a ring propeller. So a ring propeller is very much like Daphnis, only on a very, very small scale. It's orbiting in the main ring system. It's a very small moonlet, and it creates that similar wake where you have these wakes coming off the opposite edges. What's really neat about this particular set of images is because of the way the ring grazing orbits came in over the top and then exited down below, we were able to photograph the same propeller in a relatively short amount of time from both the lit side and unlit side of the rings. And so that's what you're seeing there. And scientists are interested in these because they think that they are analogous to a baby planet in a protoplanetary disk and how it can start to accrete mass in an early solar system. Okay, so now we're actually at the grand finale. This is grand finale orbit number 1. We're a day out from the first dive through the rings, and we're over Saturn's North Pole. And so we got this series of images of Saturn's hexagonal jet stream and hurricane at its North Pole. And you can see it's really neat. What's even more interesting is we have a similar set of images from 4 years earlier. And these are true color images. And you can see that the hexagon has very clearly changed from blue to this nice yellowish orange. And the reason for that is in 2013, the hexagon had only just become exposed to light. And 2017, now we're at the northern summer solstice. So sunlight's been hitting this region for a long time. And this region is full of photochemical aerosols. And so when the ultraviolet light from the sun hits them, they form a smoggy haze that turns the hexagon from blue to yellowish orange. As for why that hurricane in the center stays blue, there's a couple thoughts. One is that that hurricane is actually at a lower altitude than the surrounding clouds, and so they're shading it from the sun. So given enough time, they could eventually form a haze. However, if it acts at all like Earth hurricanes, it actually creates a downwelling that's right there, and so it's sucking any haze particles that are formed back down into the deep atmosphere. And so that keeps it that nice, pristine blue color. Okay, so a day after this, we did our first dive through the gap. And while we were doing it, we were taking images with our camera from the North Pole all the way down to the equator. And you can see the images in the lower right there. At the end of this animation, the spacecraft will actually turn because we had to go to our shielded attitude. And so you can see it turning in order to protect itself during that first crossing. We still didn't know that there was absolutely no dust there. But you can take all those images and you can stitch them together and you get a Saturn noodle. So this is a thin little strip all the way from Saturn's North Pole down to its equator. On our second dive, we were in a high rate spin to get high resolution magnetometer or magnetic field data. And here you can see the spacecraft diving through the gap, and that colored line is Saturn's magnetic field line that passes through the spacecraft. And so you can see where that field line both hits Saturn and intersects the ring plane. And that can give a lot of interesting results as far as there are particles that travel along that field line, and this kind of shows you what the source of those particles may be as far as the latitudes on Saturn or the exact distance into the ring plane that they are. On our third dive, I'm not going to go through these one by one, but the first three were pretty cool. On the third dive, we were on Earth point and communicating with Earth as we dove through. And Earth is above the ring plane relative to Saturn. And so you can see here we're pointing up above the ring plane, but as we dive through it, what that means is the signal's actually going to pass through those rings. And from that, we can look at what that does to the signal and get some information about the rings. It looks a little like this, which is a messy plot, but it's basically the transmission strength of the signal as it goes through, and it lets us see how thick the rings are, how sharp those edges are between the ringlets. Okay, so jumping ahead now to the 12th orbit, here we got a really good look, a really high-resolution picture of Saturn's B ring, which the rings are made up of mostly water ice, and if they were pure water ice, they'd probably look like this. But in this particular opportunity, we were actually able to get this image in color. And here, the color comes from impurities in the water ice. And the source of those impurities is actually still debated by the scientists. It could have been rocks and minerals that were part of the accretion disk of Saturn as it was forming, or it could have also been meteorites that are coming in and impacting the ring system and getting obliterated and orbiting with it. Okay, on the 14th orbit, a day or two after we passed through the gap for the 14th time, we looked back at Saturn, and specifically at the South Pole, and we got to watch the aurora. This is a false color image, but it's reproduced with what should be a somewhat natural color for the aurora. And so here you have Saturn as the big black body up top. You can see the starry sky sweeping by in the background and the aurora orbiting the South Pole. If you look close, you can also see that the stars sort of take a sharp right turn just before they set behind Saturn. That's because their light actually is refracted by Saturn's atmosphere as it travels back to Cassini. Okay, so next is one of my favorite observations because I actually had a hand in helping plan it, which as a mission planner I don't normally do. That's science planning's job. What we did is we were actually able to have the spacecraft as it was diving through, take pictures of the rings from the inside out, and create this movie where we got to see the lit side, the unlit side, and even neater, we got to see the entire ring system in one frame because of the foreshortening. So as you watch it go by again. So there, the entire ring system in one camera frame. Pretty neat. Okay, an orbit later, we got to watch one of the protected bodies of the Saturn system. So this is Enceladus. Again, it has that global subsurface ocean in contact with an active rocky core. And as it orbits, Saturn squeezes it, and it creates these geysers that shoot out of its south pole. So these are water geysers shooting out of the south pole. This is about 14 hours of observation, and it was taken from 500,000 miles away. So, and this was our last dedicated observation of Enceladus. Okay, grand finale orbit 21, so just 1.5 to go. We got some really great pictures of the dawn side of Saturn's atmosphere. So here you can see some of the structure in the clouds. And once again, like with the B ring, we got the images in color. And it's a little hard to make out, but you actually have these multi-hued bands of green and red in the clouds. And again, this is a true color image. That is actually what you would see if you were there. All right, getting close to the end now. On the final plunge, so this is our last half orbit, last trip from Titan's orbit down into Saturn. We took a series of 7 image sets of different objects in the rings. And so these are the final 7 sets of images that Cassini took. And this was about a day before we plunged into Saturn. Also at the end of that, we had Cassini image what would eventually become its impact site, which was a little bit morbid, but very scientifically interesting. So this gave us some context for what we would later be seeing with our other instruments as we were plunging into Saturn's atmosphere. Okay, so a little before 5 a.m. on September 15th, 2017, Cassini entered Saturn's atmosphere. And within a minute, our thrusters saturated, and we couldn't point the spacecraft anymore. It only took 20 more seconds for our S-band signal, which you can see there, to completely disappear. And within the next minute, Saturn's atmosphere destroyed the spacecraft, and Cassini became a part of Saturn. So end of mission was called at 4:56 a.m. JPL time, September 15th, 2017, when we lost the S-band carrier signal. Okay, so with that, I just want to say thank you for coming. I want to... I would also like to thank all of my Cassini family, all of my predecessors, and also everybody here who helped put this on. It takes a lot of work, and I get the easy part. I just come up here and talk to you guys. So they all did a lot of work, so give them a round of applause too. Okay, So with that, I have time for questions. However, if you want to ask a question, I ask that you go up, form a line at that microphone there. That way everybody in here can hear you, and also everybody online can hear you. And also I will preface this with, I will answer these to the best of my knowledge. If you remember those dates at the beginning, 2013 to 2017 is my reign of terror. And it went all the way back to 1991 with mission planners, and even farther than that. You know, like I said, I was a baby when it was born. So I will do what I can. I may rely on some friendly faces in the audience to help me out. So.
Well, the first one is actually kind of a remark, not a question. The birth of Cassini goes a bit back before 1982. In the mid-'70s, Donna Pivorato noticed that essentially every Mariner was different. And she said, we ought to construct some building blocks. And she proposed a project called Mariner Block 2. And then they stopped calling it Mariner because all the Mariners were solar-powered, and then later on they were nuclear-powered. But Mariner Block 2 is where Cassini got started. And, of course, Cassini was supposed to have a twin called Kraft, the Comet Rendezvous Asteroid Flyby, and that got axed long before Cassini actually got going along. So Cassini's a bit older than 1982. It goes back to the mid-'70s.
Okay, we'll have to update a couple books, and I'm going to keep telling that story because my picture before 1982 is not as good.
No pictures of before then. Yeah. Now the question I have, in the mid-'90s, before the Neptune flyby for Voyager, I asked Fred Billingsley, with such a long baseline, are the Voyager cameras good enough to do any decent astrometry, to measure the distance to nearby stars using parallax? And he said the cameras on Voyager aren't good enough for astrometry, even with that enormous baseline. Were the Cassini cameras good enough to get better parallax measurements with that enormous baseline than we can get with just using the Earth baseline for astrometry?
I don't know that we ever did that with Cassini. I'm going to look at a friendly face here.
Yeah, I don't think we ever did that.
Yeah, I think we were too busy with Saturn science. Yeah, so I'm not sure if the cameras were good enough or not to do parallax.
No star images, huh?
Right now.
We can get back to you.
Thank you.
Yeah.
I have an attitude control question.
Yeah.
It looked like the tumble boundaries that you showed for RCS and thrusters were not flat.
Right.
Why is that?
So the tumble boundary is not just a function of the density of the atmosphere. It's also a function of how fast you're going and the attitude of the spacecraft. A good way to think about this is if you're driving in a car and you put your hand out the window and put it face onto the wind and start driving faster, it's going to push you harder. Also, if you change the pointing of your hand so that it's like this, it's going to push you less. So in that one where it bumped up, we weren't necessarily going any faster. They were all about the same speed, but we were at an attitude that was more like having an open palm out the window than a closed palm out the window. And so the atmosphere turned us harder, which meant the thrusters had to fight it more.
Thank you.
Yep.
So what were some of the most difficult decisions that you had to make as a planner?
Well, I think the first one was just coming up with the fact that we could have a contingency plan and, not just Captain America it and just say, hey, shields everywhere, but to actually have to prove that, we could take data, analyze it, and make a decision and uplink a contingency to the spacecraft all within 6.5 days. Because these orbits were much, much shorter than anything we'd ever done before. The ring grazing orbits were just over a week. These were just under a week. The closest we got to that before was 9 days, and we weren't inside the ring system. So proving that we could turn something around fast enough, I think, was the biggest challenge as far as mission planning goes.
Thank you.
Yeah.
Thanks so much for the awesome presentation.
You're welcome.
How do you know how many orange peels you have left in the tank on a spacecraft?
Yeah, so that's a good question. I actually didn't say. We have some uncertainty in that estimate, right? The uncertainty in that one orange wedge was about plus or minus 1.5 orange wedges. So we really needed to, we couldn't go any longer. And so it really all comes to two things. First, it's very accurate measurements on the ground when we load up the spacecraft and take its weight. And so we have some idea with a relatively small uncertainty of how much fuel we put in it. Then that small uncertainty actually just grows and grows and grows, because from there, each time we perform a maneuver, we have a model on the ground that says about how much fuel we thought we burned, but that model has some uncertainty. So each time you use that model, what may have been a fraction of an orange wedge of uncertainty is just growing and growing and growing, such that by the end, not only is our uncertainty bigger, but the amount of fuel we have left is smaller, and so things start to look a lot scarier.
Thank you.
Yep.
I guess my question is, there must have been a lot of discussion about what to do, and there must have been some observations that would have been nice that you couldn't do. Could you tell us about some of those?
Yeah, I can tell you a little. So that's all science planning, which is right after mission planning happens. I'm the bigger picture, and then science planners go down and divvy up the individual orbits. But what I can say is that science was split up into different disciplines, and each of those disciplines and instruments were given the opportunity to say what they thought they needed in the grand finale in order to get this really great science that we were promising everyone. And luckily, when we added all those orbits up, it came out to 35 out of 22. And so that's a little bit over. But at JPL, we know how to make 35 fit into 22. we were able to get the instrument scientists together to talk things out and figure out where we could share orbits, where we could have more than one instrument on at the same time and both get the same science. And then we also had to push back a little bit and say, do you really need that many orbits? Could you do with one less? And so it was just a series of negotiations with the project and the science teams that went back and forth like that to get it all fit into the 22 and a half orbits.
Thank you.
Yeah.
Hi. My question would be for future missions, what sort of guidance do you have for people that will be in your shoes 5 years, 10 years, and 15 years from now? What sort of, maybe you can think of like one or two or three things what sort of guidance do you have for them learning what you learned on this mission, where it seemed like there were a lot of options that you may not have thought that you had, that you did have?
Yeah. So the first one is plan for what you think you're never going to do, because you're going to do it. We never thought we'd fly inside the ring system. And so being able to do that was actually a big deal. It took a lot of work. We had to change a lot of tools in order to actually get them to function inside the rings, because we never thought we'd be there. But what that really gets to is, I'd say a couple other lessons. It's you got to keep the spacecraft simple and robust. And that makes it so that you have something that lasts a long time so that you can just keep doing this great science. And then also you need to keep your system flexible so that you can react to new discoveries and going new places. And so I think those are the two key things about the Cassini spacecraft and the project that made it so that we could do this.
Gotcha. Thank you so much.
Yeah.
How come some of the pictures that Cassini took were black and white and others were color?
Yeah, so Cassini's cameras actually are just black and white. And the way it works is we put different color filters in front of them so that just that color of light comes through. And depending on the science we're doing and how much time we have, that determines how many filters we're able to put in front of the camera when we make a given observation. In order to get one in color as we see it, we need 3 filters, the red, the green, and the blue. And so for those particular ones, we were able to get all 3 filters in front of the camera and reproduce true-to-life images.
Hello, thanks for your lecture tonight.
Yeah.
You showed a beautiful picture of the moon Daphne going through the ring plane.
Yeah.
How big is that moon in comparison to ours or something else that we can reference?
Oh,
I think it's about 150 miles across.
okay. My friendly face says that it's about 150 miles across.
So it's tiny.
It's tiny, yes.
Thank you.
Yeah. Okay, I'm getting some blue card questions from online, but yeah.
So as Cassini gets extended over all these years, does it have an arc? Like, did you know you were going to dive into the rings all these years later as it gets past, the mantle gets past, they making up new missions as they're seeing what kind of science they're gathering? Could you talk a little bit about that?
Yeah, so I think it was 2008 or 2009 when we first thought of doing this grand finale. So, 8 or 9 years before it. As far as how Cassini kept getting extended, we'd submit a proposal and go through a review process every 2 years. And that would say, hey, here's what we're doing, here's our status, here's all this great stuff we did, and if you give us this much more money, here's this much more great stuff that we think we're going to be able to do. And so it was sort of on this rolling 2-year basis that we were able to try and plan out what the next 2 years would be.
Thank you. I'm just in awe of what humans can do. So
Yeah.
thank you.
Okay, so now we have questions from online. So this one's from YouTube from One Heart. How small could Cassini be made with today's technology? Actually, interestingly, I don't think it could be made too much smaller. Yeah, that graphic that I showed you where it was filled up with propellant, yeah, that wasn't accurate, but it was a lot closer to accurate than you may think it was. Most of that spacecraft body that you see there is filled with fuel, and so that's really where it gets its size. The other thing that sizes it, I'd say, is the antenna up on top. And Saturn hasn't gotten any closer to Earth as far as I know. And so this antenna would need to be about the same size in order to communicate with Earth. So the part that would get smaller, if you look at the spacecraft, this ring going around the top below the antenna but above the probe, that's where all our electronics are, and those could probably get a little bit smaller. Okay, yes, taking them from here we go. Okay, also from YouTube, from Astronomy Nation. Was the contamination of Titan by the Huygens probe taken into consideration? Yes. So we knew that the Huygens probe was going to Titan. And so we built it with that in mind. And so it went through a much more stringent planetary protection process than the orbiter did. And so that made it safe to go down to Titan. But Cassini, it's very expensive to do that. And so Cassini was not built to those standards. It wasn't going to go down to Titan. And so that's why it could not be crashed on Titan. Okay, YouTube from Eric Lamplanta. What was the biggest surprise that came out of Cassini's discoveries? I think this is an opinion, but in my opinion, the biggest surprise was Enceladus. I don't think anybody expected to find this global subsurface ocean that actually had like activity where you have these jets coming out of the South Pole, and then we later find out, hey, it's in contact with a rocky core, and guess what? We think there's actually evidence that there could be the chemicals in that ocean necessary to support life. And so that is definitely by far the biggest surprise. Also because the Enceladus at Saturn is very much like Europa at Jupiter. It's almost identical in that it's an icy moon with a subsurface ocean in contact with a rocky core. And discovering two of these in one solar system means that these potentially habitable environments outside of the sun's habitable zone are not rare. If you have it twice in one solar system, it means in the whole universe it could be occurring a lot. So it really increases the probability that we could someday find life beyond Earth. Okay, and YouTube from Claudia. What kind of cameras were on Cassini? So the cameras on Cassini were basically telescopes. So, like I said, that one picture of Enceladus was taken from 500,000 miles away. So the cameras are digital cameras. The highest resolution one is like 1 megapixel? Yeah, 1 megapixel camera. It was launched in '97. You know, give us a break. Yeah, but then it has this huge lens put on it so that the fields of view are really, really small. Like you could not use them in this room. You know, it'd be like using binoculars in your bedroom. You're not going to see a whole lot. So that's what it was. It was a 1 megapixel telescope. All right. Any other questions from the room, from online? Oh, I'll repeat it. Yes.
What's the baud rate that data was transmitted at?
Okay, so he asked what the baud rate or the data rate that Cassini was able to transmit at. And again, I'm going to look at my friendly face.
Look at your other friend.
Yeah.
That one back
yeah. I have another friendly face. You want to come to the microphone?
So the highest data rate we could transmit at was 142,000 bits per second from 1 billion miles away.
Yeah.
It may not seem like fast, but
Yeah.
from 1 billion miles away, that's doing pretty good.
Okay. If there are no more questions, you're still welcome to stay here. You'll be warm and dry.
How big was your Cassini team? And I'm talking your dates when you were planner. How many people?
When I was the planner, I think we had 50 to 100 part-time people. We didn't have a whole lot of full-time, but
Well, there's 250 scientists.
oh, sure, yeah, sorry, yeah. the project, yes, the project people at JPL, sorry, the project people at JPL. I believe there are about 100 part-timers that all fit into about 50 full-time equivalents. All right, you can clap again if you want.
Outstanding, Eric. Yes, the fuel one, that's a winner.
Our next mission to Jupiter is actually going to be solar powered.